Okay, so we now look at the ninth exercise. If you recall, when we defined arbitrary intersection of a non-empty family of sets, there we came across the point that, okay, let me just put it like this. Say there is a set I, and for each element alpha in I, there is a set A alpha. Then this collection is a family of sets, and I is the index set. The family is being indexed by the levels in I. So in that sense, it's an indexed family. Then we defined the intersection of this indexed family, provided of course I is non-empty. That condition is there, we assume that. Okay. Now the intersection has been defined like this. First, we arbitrarily choose a label in the index set, then we define this intersection to be the set of all elements in A beta such that X belongs to A alpha for all alpha in I. So this was the definition of the intersection. And there we made the observation that this clearly depends on the choice of this label beta. What happens if we choose another label? Shall we get a different intersection? Because then the concept will not be well defined. Fortunately, that is not the case. We will have the same set irrespective of our choice of the label, and that's what we have to show here. So we are given an index set, and we have chosen two different labels, beta and beta, not necessarily different, but just two labels, beta and beta prime. And it's also given that for each label in the index set there is assigned a set. Then this definition of the intersection which we get after choosing beta and the one that we get after choosing beta prime, they are to be shown the same set. Okay, so let us see the solution. So the procedure is our standard procedure. We have to show that two sets are equal. So that means we have to show that each is a subset of the other. So let us first show that this is a subset of this. So let Y be any element in the first set A beta such that X belongs to A alpha for all alpha belonging to the index set I. Then Y belongs to A beta and Y belongs to A alpha for all alpha belonging to I. Now, since alpha is any index or any label, in place of alpha we can choose beta prime. In particular, Y belongs to A beta prime. So Y belongs to A beta prime, and this continues to be true, Y belongs to A alpha for all alpha. Which implies Y belongs to this set. for all alpha belonging to I. That means the first set is a subset of the second set. Hence, for all alpha belonging to I is a subset of this second set. Similarly, one can prove the reverse inclusion. We may as well write that. Hence, and the solution ends. So in spite of arbitrarily choosing a label and then using it to define the intersection, actually we end up getting the same set irrespective of the choice of the label. Okay. There is one, actually this is not where the exercise ends. An additional line is there. Also, explain why equation 3.4 is true. And equation, although we have not used numbers to number the equation, at the end of the concept of intersection, we noted this: x belongs to this intersection if and only if x belongs to A alpha for all alpha belonging to I. This is equation 3.4. We are being also asked to, so actually the solution does not end here, but I am deliberately ending it here because I am going to leave this to you. See, one side of the double implication is obvious. If x belongs to this intersection, then definitely x belongs to A alpha for all alpha belonging to I. Why? Because by the definition of intersection, that is a condition. What happens when we have to come from this statement to this statement? Okay, that I leave to you to figure out. Okay, with this exercise ends. Now after this we have the 10th one. Suppose that we need ink. suppose that I and J are two sets. So two index sets, and for all alpha belonging to I union J, let A alpha be a set. Okay, so it's not I and J, they are not index sets separate. I mean, they can be considered as index sets separately, but for all labels alpha in I union J, there are sets A alpha. So the family is indexed by I union J. If you restrict your attention to only I, you will get a subfamily of sets of that family. Okay, now show that let me write it here. Union A alpha, alpha belonging to I, union A alpha, alpha belonging to J is equal to union A alpha, alpha belongs to I union J. We have to show this. Union of two arbitrary unions is again an arbitrary union of that form. And just like that, there is one statement involving intersection. But for that, there is an additional restriction. You already know that we can only form the intersection of a non-empty family of sets if I and J are non-empty, that is, both are non-empty. Show that is it still, no, it's intersection. Intersection A alpha, where alpha varies over I. Intersection A alpha, alpha varies over J, equals intersection A alpha, alpha varies over I union J. It will not be very difficult to prove these things, only we have to be careful about what we are doing actually. So we first prove this one. Let X be any element in this set on the left hand side. Then this implies, let me use, instead of writing this implies, so hence, let me just use the logical symbol. This implies X belongs to, by the definition of this union of two sets, because these are two sets, this belongs to the first set, or X belongs to the second set. That implies X belongs to A alpha for some alpha belonging to I, or from this one we get x belongs to A alpha for some alpha belonging to J. This implies x belongs to A alpha for some alpha belonging to I, or alpha belonging to J, and this implies x belongs to A alpha. So either this is true or this is true, or both are true. If this is true, then x belongs to A alpha for some alpha belonging to J. If this one is true, then x belongs to A alpha for some alpha belonging to, I have written J on both of the things, right? One of them is I and the other is J. Okay, so that means in any case x will belong to A alpha for some alpha belonging to I union J, because if alpha is in I or alpha is in J, then it has to be in I union J, and that's why x belongs to this. Now here itself we can try to see if the converse is true. You choose any element in this union. So we are now considering an element in the second set. This means x belongs to A alpha for some alpha belonging to I union J by the definition of this union. That means x belongs to A alpha for some alpha. Since alpha is in this union, alpha will either be in A or either be in I or J or both. So that means from this you get this. From this we can write this statement like this. So we can see that the steps also work in the other direction. And if we write the argument like this, then we cannot write let. We will write note that. Note that this statement is equivalent to this statement. So here we have not only proved that this is a subset of this, but this is also a subset of this. So we can conclude like this. Hence, and simultaneously this is also a subset of this. So the first one has been proved. Now we prove the second one. Next, okay, for the second one, can we go similarly, or do we have to do it separately? Let us first start to be on the safe side. Let us first start by showing that this is a subset of that. Let Z be any element in this intersection of two intersections. then Z belongs to the first intersection and Z belongs to the second intersection. This implies Z belongs to A alpha for all alpha belonging to I. Note that we are writing just this without choosing any beta in I and then saying things like that, because this is I can make this conclusion because of that equation 3.4. You go back to that, the one that we mentioned in the previous exercise. There itself we said that this is equivalent to this, and Z belongs to A alpha for all alpha belonging to J. That means for all levels in I, Z belongs to A that level, and just like that for any level alpha in J, Z belongs to A alpha. Thus, Z belongs to A alpha for all alpha belonging to not just I but J. That's why we have a union here. Don't make the mistake of writing intersection, because you see so many intersections. That does not mean this also has to be an intersection. This is the union, because for all levels in I, something is happening. Also for all levels in J, something is happening. So that thing will happen for all levels in I as well as J. So I union J. Which implies hence okay, so one part of this second equality is over. Next, we consider an element here and figure things out. Now, let U be any element in this intersection. Then U belongs to A alpha for all alpha belonging to I union J. This implies U belongs to A alpha for all alpha belonging to I, and U belongs to A alpha for all alpha belonging to, so there also we could have argued just like that there itself. Anyway, let us just follow the way we are going through this solution for all alpha belonging to J. This in turn implies, it's not X, U belongs to A alpha for all alpha in I, that means U is in this intersection. and u belonging to A alpha for all alpha in J means u is in this intersection. Hence, intersection, the one involving J, and we have so we now combine these two containment relations and get our final equality. And this completes the solution. To make sure that these intersections make sense, we had to consider that I and J are non-empty. Okay, so this was the 10th one, and then there is only one more, and this set of exercises will be over. Union and intersection we have seen in terms of arbitrary families. We will now see difference of two sets. So this is the 11th one. Let X be a set. Let I be a non-empty set. And for all alpha belonging to I, let A alpha be a subset of X. That means now we have a family A alpha which form a subset of the power set of X, because each A alpha is a subset of X, an indexed family of subsets of X. Show that so these are the general form of De Morgan's laws. X minus union A alpha, alpha belongs to I, equals intersection of X minus A alpha and a similar one with union and intersection switched. After that there is a remark. This should be compared with De Morgan's laws. In proposition 28, 3128. Although one cannot derive the above, oh, it's raining, I think, above identities directly from De Morgan's laws. As I could be infinite. De Morgan's laws, they deal with two sets, right? However, those laws can be extended to any finite number of sets using induction. But here the family I can be an infinite family. The set I can be an infinite set. As such, the family of sets A alpha will be an infinite family of sets, potentially having infinite number of distinct sets. So these things cannot be proved using De Morgan's laws. They have to be proved on their own. Okay, so let us solve this final exercise. Here also the solution is not very difficult. We just have to keep track of the things and see what is happening carefully. So first we prove this one. Let X be any element in the first set. Then X belongs to X and X does not belong to union A alpha, alpha belonging to I. Now we have to understand what this condition says. We have a number of sets. They may or may not have some very complicated intersections in between them, say A1, A2, A3, etc. Although I is not necessarily a set of natural numbers, but just for the sake of showing you, or if you want, we can have general indices here. Alpha 1, alpha 2, these are coming from I, alpha 3. X does not belong to their union. So do you think X can belong to any one of them? Definitely not, because then it would belong to the union. That means this not belonging to the union means X does not belong to any A alpha. That is, X does not belong to A alpha for all alpha. That's the conclusion. So we are going to write that. That is, X belongs to X and X does not belong to A alpha for all alpha belonging to I. This implies X is in X and X is not in A alpha for all alpha. That means X belongs to X minus A alpha for all alpha belonging to I. Note that we have for all, so we will have intersection. Hence, X belongs to intersection X minus A alpha, alpha belonging to I, and we have X minus union a subset of this intersection.